Alright, today we're going to be talking about continuums. Continuums are probably something that you've seen in your everyday life. It is something that we use actually a lot, so it's very relatable in chemistry and then also in your everyday life. So here's some examples of some good continuums. How are you feeling today? I am sad and I am happy today. I'm going to put down that I'm like an 8. The snow kind of brought down my mood, but we got a new dog, so that really makes me very excited, so I'm pretty happy. I hate the Packers. I love the Packers. Where do you feel on that continuum? I'm going to say I'm about a 9. I really like the Packers. I watch them most weekends when they're playing. How about how much do you text? I don't text at all. I text a lot. I'm going to give myself about a 7. I'm not constantly texting, but it's usually my main form of communication with friends and family. How about how fast do you run? I run slowly. I run fast. I'm about at a 5. I don't really run really fast, but I'm not super slow, so I'm like right in the middle. So between like 4 and 6, you're right in the middle. Does it really matter? Nah. Alright, so what is a continuum? Basically, it is a rating scale that shows something can change. So it's a rating scale that shows how something can change. Give an example of another continuum. I'm going to give you a couple seconds to think about another continuum that you probably have seen in your everyday life. Does anyone do online shopping? You know, you look at the reviews, you know, a 1 to a 5-star review on clothes, on restaurants, for movies. Those are all very common continuums that we see every day in our life. I know I base quite a few of my decisions off of ratings. Do I want to go to that restaurant that has a 2-star rating? Probably not. I'm going to pick the restaurant with a 4 or 5-star rating, right? But remember that 1 doesn't always mean bad and 5 doesn't always mean good. Either end of the scale can mean a different thing. Alright, so we've been talking about chemical bonds a lot, and those are actually an example of a continuum. The continuum that we're going to put chemical bonds on is between covalent and ionic. Remember, ionic don't share their electrons. They steal those electrons from the nonmetal. The nonmetals steal the electrons from the metals. They don't share. And with the covalent, the nonmetals share those electrons. So, about the rating scale that we're going to use is 0, 0.4, 1.7, and 3.3. So, over on this side, below 0.4, you're pretty safe bet that that is a covalent compound. If you're above that, probably an ionic compound. Something else we've just talked about when we talk about chemical bonds on a continuum is electronegativity. Okay, so this measures the ability of an atom to attract a bonding pair of electrons. So we see that base there, electron, negativity. So it's the ability to attract those negative electrons. All right. Then we're going to talk about our periodic table a little bit. We have an even fancier periodic table. How about right here? It's the electronegativity scale. As you can see, each element is given a rating. You can see nonpolar is below 0.4, polar covalent is 0.4 to 1.7, and 1.7 to 3.3 is ionic. All right, so we can see some trends going on here, right? From top to bottom, so if we're starting up here in any column here, and as you move down, your electronegativity is going to tend to decrease. You can see that really well in our halogens, 4.0, 3.0, 2.8, it just keeps decreasing. And over here in our column 1, it does that as well. As we are moving across the periodic table from left to right, like you're reading, they increase. Okay, we can see that because remember those metals, they give up their electrons to these nonmetals over here. So that just makes sense. All right, let's go in and fill this chart out now that we've seen that. So, a group trend from top to bottom, we said that decreases. And this is because as you go down your groups or your columns, you're getting larger and larger atoms. You're adding more electrons and making that electron shell bigger and bigger and bigger. And those outside electrons are going to be further away from the positive inner nucleus. So the nucleus is positive in the middle. So let's draw that at the bottom here. So we have a positive inner nucleus attracting, we have a positive inner nucleus attracting these electrons that are on the outside. As you add more and more rings of these electrons, it gets harder for them to get attracted to that inner positive, right? The further away you put magnets, the less attracted they're going to be. So, bigger atoms are harder to attract electrons. All right, and I'm going to abbreviate that with an E minus. Okay. As we go from left to right across the periodic table, remember from the metals across to the nonmetals, it's going to increase. The electronegativity increases across the periodic table. This is because you have more of those positive protons in the same sized shells. So there's going to be more positives to attract those electrons in this about the same size atom. All right, so it's a smaller atom with more protons is easier to attract those electrons. Okay, remember E minus is electrons. All right, we're going to flip over to the back here. So now we're going to talk about the different types on that continuum. Okay, remember if it falls below 0.4, it's what we call that nonpolar covalent. So this is a perfect equal sharing of those electrons. Okay, so this picture here, the field around it is, the bigger the field, the more electrons are around. Okay, so you can see this is very even around these two, these are the nucleuses. So these are those positive nuclei. And you can see that the shape is very even around both. Neither is hogging. They're doing a really good job of sharing. So it's like if you had a candy bar and your best friend was like, oh, that looks really good, and you really like that person, so you're going to give them exactly half. So it really does good at sharing. So because the electrons don't hang around one nuclei or the other for very long, it's very equal. this is going to have no charge. And we knew that. It's a covalent compound, and we say that they don't have any charges. Things start to get a little funky when we go to something called a polar covalent compound. Okay, polar covalent. It's a type of covalent compound where it's not exactly as good at sharing those electrons. Okay, as you can see, this side is taking those electrons a lot more than this side. Okay, so this isn't, they're still sharing, but it's an unequal sharing of those electrons. All right, if you have brothers and sisters, you might know what I'm talking about. You get a candy bar, and your mom or your dad or your guardian, whoever, is like, you should share some of that with your little sister or little brother. You're like, ugh, I don't want to share it. But you're like, okay. So instead of giving him that whole candy bar, or exactly half, I'm going to break off just a little bit of it and give it to him. So then I get more. Because they're kind of annoying and I don't really like them that much. Okay? So, when it's an unequal sharing of those electrons, these electrons tend to hang out around this nuclei more. And it gets what we call a partial positive charge. See that little sigma, the lowercase sigma there? And a lowercase positive sigma, those indicate those partial charges. All right, so we're going to call them partial charges. All right, and then you know this last one. This is a complete transfer of electrons for those ionic. They don't share at all. They're really greedy. Be like if a stranger came up and was like, "Can I have some of your chocolate?" And you're like, "No. You're not sharing your candy bar." Okay? So these have the full charges, which we have been drawing pretty much all week. All right. So when we're talking about those polar covalent compounds and these partial charges, this one here, there's a special name for those partial charges. It is called a dipole. Di meaning two, and pole referring to either end of the compound. So this is a pole, and this is a pole. So two poles. So it's a separation of a positive and a negative charges in a polar covalent molecule. This is similar to like the opposite poles of a magnet. You know, you have the south and the north end, and you can't stick them together. You can't stick the two south ends together because they both have the same charge. All right, and how do we represent these? There's two ways you can do it. Either way, completely correct. In this picture is one way. We do that little lowercase sigma positive and lowercase sigma negative. All right, or you can use a dipole arrow. Okay, so it's going to look something like this. This goes from the lower electronegativity to the higher. I'm just going to abbreviate that EN. Okay? So you can see that plus kind of represents the positive sigma, the positive dipole, and then the arrow is showing where the negative is. All right. And I hope you guys are fans of math, because there's a little bit of math involved here. All right? And you get these numbers from our lovely electronegativity table. Okay? There is one on BB9. There's one linked in the agenda. You can go get that. You can probably type in electronegativity periodic table in Google, and it'll pop up for you. Okay? So, how do we do this? We have oxygen, and we're going to go and find oxygen on our electronegativity scale. oxygen is right here, and it's right here, and it has an electronegativity of 3.5. Okay, then we're going to go and find hydrogen here, 2.1. All right, so it doesn't matter which order these are in here. When you're doing the electronegativity, you're always going to subtract the smaller one from the larger one. So the bigger one goes first, 3.5 minus 2.1 equals 1.4. Okay? So, now we go back to our lovely scale here. So, this is polar covalent, this is covalent, non-polar covalent, and this is ionic, okay? So, this is between 0.4 and 1.7. Yes, so it's polar covalent. Okay, and now we have to draw it with the charges. Okay, so you can do it one of two ways, OH, and this one had the larger you can't see that. Okay, OH. This one has the higher electronegativity, so it is going to get the negative charge. And this had the lower electronegativity, so it gets the positive charge. All right? When you are drawing charges or partial charges, always try to put them at the top of the molecule, at the top of the atom. That's just kind of where they go in chemistry, so if you can remember that, put them at the top. It's a nice way so that I can see exactly where it is and I don't have to go searching around. Just a common way to do it in chemistry. All right, if we're doing it the other way, I'm going to put the H first just for fun. And we're going to show that this has the higher electronegativity. I'm sorry, this is incorrect. Let's try that again. H first, and the plus goes at the lower electronegativity, so it goes this way. All right. Sometimes I make mistakes. We just correct them and move on. So we see H has the lower electronegativity, so it gets the plus, and then the arrow moves towards the oxygen. All right, let's do one more together. Go find calcium. It's 1.0. Fluorine, 4.0. It is the highest, has the highest electronegativity on the entire periodic table. All right, so remember we're going to put the bigger number first. 4.0 minus 1.0 equals 3.0. So we're going to go back to our table over here. Is it between 1.7 and 3.3? Yes, so that means it is ionic. All right, and remember we're not drawing dashes in ionic. This has charges, full charges. So Ca, F, and Ca gives 2 electrons to fluorine, so it becomes a -2 and a +2. Okay, we're gonna do this whole sheet so you can get practice, and then there is a practice sheet for you on BB9 in Google Classroom. All right, C, 2.5, H, 2.1, bigger one first, equals 0.4. Go back here, it's 0.4, which lies under nonpolar covalent. So we're going to do an NPC. So there's no dipole moment, no partial charge on this. They share relatively equally. They're going to look like this one up here. Okay? Remember, this is a continuum, so it falls somewhere along that line. All right? And no, this is not a complete molecule. Remember, C isn't happy, but we're just focusing on 2 atoms together at this point. We're not looking at whole compounds. All right, BR, bromine on bromine. That is a 2.8. And it's the same molecule, so it's going to have the same electronegativity. Well, 0. And 0 is absolutely nonpolar covalent. So it is, there are no dipoles on this. There's no partial charges. It's a completely covalent, nonpolar covalent compound. All right? Anytime you see two of the same elements together, it's most likely going to be nonpolar covalent as long as they are nonmetals. All right, awesome job. You can get started on this page here, types of bonds. Gives you lots more practice on everything we've been doing this week, plus then adding in these charges and partial charges. All right, I hope you have a great rest of your week.